Imagine a nuclear reactor designed to move. Not a massive power station built over decades. Not a plant connected to a vast network of transmission lines. But a compact, transportable reactor designed to deliver electricity where conventional infrastructure may not exist. This is the ambition behind Project Pele, a United States Department of Defense program developing a 1.5 megawatt transportable nuclear microreactor for military missions. Today, Pele is still a demonstration project. But its implications could reach far beyond the battlefield. Because if engineers can build nuclear power that is mobile, resilient, and capable of operating independently from the traditional grid, one question becomes impossible to ignore. Could the technology developed for military bases eventually help power the cities of tomorrow? For more than a century, nuclear power has followed a familiar model. Build a massive plant. Construct extensive infrastructure. Connect it to the grid. And keep it operating in one location for decades. Project Pele explores a radically different approach. The program was launched by the U.S. Department of Defense to develop a safe, mobile, advanced nuclear microreactor capable of supporting missions where reliable electricity is difficult to provide. The prototype is designed around a 1.5 megawatt power system. That is tiny compared with a conventional commercial nuclear power station. But that is precisely the point. Pele is not designed to replace America's largest power plants. It is designed to bring dependable electricity to places where building a conventional plant, or relying entirely on long-distance transmission, may be impractical. The prototype is being developed as a transportable system. According to its industrial partner, BWXT, the reactor and associated systems are designed to fit into 4 20-foot shipping containers. The concept is built around mobility. Road, rail, sea, and potentially air transport. The vision is simple. Instead of building the power plant first and waiting for the grid to arrive, the power plant itself can travel to where the power is needed. But the technology behind that vision is where the story becomes even more interesting. Project Pele uses TRISO fuel. TRISO stands for tristructural isotropic particle fuel. Each tiny fuel particle is surrounded by multiple protective layers designed to contain radioactive material at extremely high temperatures. This does not mean the reactor is literally meltdown-proof. But the fuel's robust design is intended to provide a strong barrier against the release of radioactive material under extreme conditions. And that is one reason advanced microreactors are attracting attention. They are not simply smaller versions of traditional nuclear plants. They represent a different philosophy. Smaller. More modular. Potentially more flexible. And designed for missions where conventional infrastructure may be difficult to build or protect. But Project Pele remains a demonstration program. The prototype still has to undergo testing. The real question is not whether the concept sounds revolutionary. The real question is whether it can work reliably in the real world. Now imagine the opposite of Project Pele. A power system that depends on thousands of miles of transmission lines, hundreds of substations, millions of pieces of equipment, and a network connecting almost everything together. This is the modern electrical grid. It is one of humanity's greatest engineering achievements. But it is also incredibly complex. Extreme weather can damage transmission infrastructure. Wildfires can force utilities to shut down lines. Hurricanes can destroy substations. Equipment failures can cascade across interconnected systems. And cyber attacks represent another category of risk. The challenge is not that the grid is constantly failing. It is that modern civilization has become completely dependent on it. Hospitals need continuous electricity. Water treatment plants need pumps. Emergency services need communications. Data centers need uninterrupted power. And cities need electricity for almost every basic function of modern life. This is where microgrids enter the story. A microgrid is not necessarily nuclear. It can combine solar panels, batteries, natural gas generators, wind turbines, and other energy sources. Its defining feature is its ability to operate independently from the larger grid when necessary. This is called islanding. Now imagine adding a compact nuclear reactor to that architecture. The reactor would not necessarily power an entire metropolitan area. Instead, it could potentially provide a continuous source of baseline electricity to a critical microgrid. A hospital. A military installation. A water treatment facility. An emergency operations center. Or perhaps an industrial site. The idea is not to eliminate the national grid. It is to create layers of resilience. If the main grid fails, critical systems could continue operating. But here, the distinction between fact and future becomes essential. Project Pele has not been deployed to American cities. There is no verified program currently placing Pele reactors in downtown neighborhoods. The civilian application is a possibility to be studied, not a reality already happening. And even if the technology succeeds technically, a civilian deployment would face another challenge. Regulation. Building a reactor is only half the challenge. The other half is permission to operate it. Nuclear power is among the most heavily regulated industries in the world. And a mobile reactor introduces new questions. Where can it operate? Who controls it? How is it secured? How is it transported? What happens during an emergency? Who is responsible for the fuel? And how should regulators oversee a reactor that may not remain permanently attached to one location? The U.S. Nuclear Regulatory Commission has been actively examining these questions. The NRC says microreactors can already be licensed under existing frameworks. At the same time, the agency has been working toward regulatory approaches specifically designed for the unique characteristics of microreactors. The 2024 ADVANCE Act directed the NRC to develop risk-informed and performance-based strategies for microreactor licensing. And in 2025, the agency began developing a proposed framework known as Part 57 for microreactors and other reactors with comparable risk profiles. The goal is not to remove safety regulation. It is to create a regulatory system that reflects the characteristics of smaller, potentially lower consequence reactor designs. That distinction matters. Because the future of microreactors will depend on more than engineering. It will depend on public acceptance, security, emergency planning, transportation, waste management, fuel availability, insurance, and economics. In other words, Project Pele may demonstrate whether a mobile nuclear reactor can work. But commercial deployment will require proving something much larger. That society is ready to live with one. So what happens if Project Pele succeeds? The answer is not necessarily a city filled with nuclear reactors. The more realistic possibility is selective deployment. Imagine a future hospital microgrid. Solar panels cover the rooftops. Batteries handle short-term fluctuations. A local microreactor provides steady power. The national grid remains connected. But if the grid goes down, the critical facility continues operating. This is the concept of layered resilience. And it could extend beyond hospitals, water treatment plants, remote communities, industrial facilities, military bases, research centers, data infrastructure, disaster response hubs. In each case, the value would not necessarily be cheap electricity. It would be reliable electricity. That distinction could become increasingly important. A power outage lasting several minutes is an inconvenience. An outage lasting several days can become a crisis. For critical infrastructure, the economic value of uninterrupted power can be enormous. But there is another reality. A Project Pele prototype produces only 1.5 megawatts. That is nowhere near enough to power an entire major city. So the future would likely involve networks of technologies rather than one magic reactor. Large nuclear plants for bulk electricity. Solar and wind for renewable generation. Batteries for short-duration storage. Hydrogen or other technologies for longer-duration needs. And potentially microreactors for locations that need continuous, resilient power. The future energy system may not be centralized or decentralized. It may be both. A national grid, supported by thousands of local energy islands. And Project Pele could become one experiment in that much larger transformation. There is a deeper question hiding behind Project Pele. Energy independence. For decades, cities have depended on infrastructure stretching far beyond their borders. Fuel arrives from somewhere else. Electricity travels across distant transmission lines. And a disruption in one part of the system can affect another. Microgrids challenge that model. They ask a different question. What if critical energy needs could be secured locally? This does not mean complete energy independence. No city is truly disconnected from the global economy. Fuel, equipment, maintenance, technology, all still depend on supply chains. But resilience is not about eliminating every vulnerability. It is about reducing the number of ways a single failure can bring everything down. This is where microreactors could become strategically interesting. A reactor capable of operating for extended periods without frequent refueling could provide a stable energy foundation. Renewables could provide additional generation. Batteries could manage rapid fluctuations. And the wider grid could remain available when conditions are normal. The result would be a system with multiple layers. If one fails, another takes over. But there is a major caveat. The economics are still uncertain. A microreactor must compete with conventional generators, renewable energy, batteries, and other technologies. It must also pay for licensing, security, construction, fuel, maintenance, decommissioning, and waste management. So the future question is not simply, can we build a portable nuclear reactor? Project Pele is already attempting to answer that. The harder question is, can we build one that makes economic sense for civilian society? That answer has not yet arrived. Now imagine the year 2040. A massive storm strikes a major metropolitan region. Transmission lines fail. Thousands of homes lose electricity. But inside the city, something different is happening. Hospitals remain operational. Water treatment continues. Emergency communications stay online. Data centers maintain critical services. Not because one technology saved the city, but because the city was designed with resilience in mind. Solar, wind, batteries, backup generators, advanced nuclear, and intelligent microgrids. The national grid still exists. But the city is no longer completely dependent on it. This is the future that Project Pele makes us consider. Not necessarily a world where every neighborhood has a nuclear reactor. But a world where energy infrastructure becomes more modular, more distributed, and more resilient. The military often develops technologies for the hardest environments. Remote bases. Harsh climates. Disconnected locations. The civilian world sometimes learns from those innovations later. Whether Project Pele becomes one of those technologies remains unknown. The prototype still has to be tested. Regulators still have work to do. And the economics must still be proven. But the experiment has already begun. A nuclear reactor designed to move. A power plant designed to travel. And perhaps, a glimpse of a future where electricity no longer has to come from only one place. Because the ultimate energy revolution may not be about generating more power, It may be about making sure that when the unexpected happens, the lights stay on. Project Pele may never become the nuclear reactor that powers a city. Or it could become the beginning of something much bigger. A new generation of mobile, modular energy systems. What do you think? Could advanced microreactors become part of the future of civilian cities? Or are the risks and costs simply too high? Tell us what you think in the comments. If you enjoyed this documentary, like the video, subscribe to Flying Art Films, and turn on notifications. Because the future of energy is already being engineered.